Hello, this lesson is on section 2.3, getting information from a graph of a function, and there's a lot of things to go over. The first one's kind of a review. Given a graph, you should be able to find the domain. Some things that I did off camera. These gray dots are really solid, but there is a hole right here, and it's a little confusing. It said 2, 0, but really there's nothing there. Really what's happening is when x is 2, there is no value of y. Okay, so there's a hole there. The location was written as 2, 0, but that's a little more clear. Okay, so now if we want to determine the domain of f of x, we can look at the x coordinates. That's what domain is. So that would be bracket -5, because when x is -5, there is a y coordinate, all the way till we get to 2, which we have to go all the way to 2, but to let people know that 2 is not included, you put parentheses. So that's the domain. And the range is the set of y coordinates in the graph. So the lowest y coordinate is bracket -7, and it goes all the way up. All of these are y coordinates, and the highest y coordinate, there is no break in the graph. You might say, well, there's a hole here. Well, there's a y coordinate of 0 here, there's a y coordinate of 0 here. So we can keep on going all the way up to 3.38 bracket. All right, example 2, I put arrows on the end. These graphs are created by Desmos, so it doesn't do arrows. So when it just goes off the page like that, we assume it goes on forever. And so this happens to be a graph of a parabola. The domain is the set of x coordinates, and this is going up in a diagonal direction, which means it's gonna collect more and more x values to the left and the right. So this domain is all real numbers, or -infinity to infinity. There is a restriction on the range because there is a lowest y value. So the range of this parabola is from -5 up to infinity. So that's review. All right, now let's do something new. So when you're given a graph, I can ask you something like this. A function greater than 0 a function is greater than 0 when its graph is above the x-axis, and less than 0 when the graph is below the x-axis. So I could ask you, on what interval is f of x greater than 0, and on what interval is f of x less than 0? So this is very specific to 0, but what's happening is it can be any number, but we start out with 0. So what's happening is we want to know, this is saying what interval, we want to know what x's make y, that's f of x, that's y, behave this way. What x's make y greater than 0? And that's a trend that's important to remember throughout the life of your study of functions. The x's are the inputs. They are what makes the outputs behave. So the only time you're ever going to be writing down y coordinates is when you're talking about the range. Every other time, 100%, it's going to be the x's that you're going to write down, because the x's make the y behave the way it does. Okay, so when you hear a question on what interval is f of x greater than 0, what you can do is first say, well, let's see where y equals 0. And that's a horizontal line through 0. So that's why this is specifically talking about the x-axis. Okay, so where are the y's greater than 0? Well, if you think about this y-axis, the y coordinates are greater than 0 when the graph is above the x-axis. The y values are positive right here. So you do have to locate where the y's are greater than 0. But then remember, you got to make that change, and this is where it gets difficult. You want to write down the x's that are making that happen. So the x's that are making that happen start here at -2. That's where y equals 0. So I put an open hole there because I don't want where y equals 0. I want it where it's greater than 0. And these x's When x is -5, y is positive. When x is -4, y is positive. All of those x's make those y's positive, greater than 0. And these x's over here, starting with, this is 1, x equals 1. So that's what we're going to write down in interval notation. So the answer on what interval is f of x greater than 0 are these x's, from -infinity to -2, parentheses, union 1 to infinity. Again, parentheses, because I don't want to know where y is greater than or equal to 0, just where it's greater than 0. All right, so the same thing can be done if it says on what interval is f of x less than 0. We're still talking about the x-axis, and these y's are less than 0. And the x's that make it happen are the x's from -2 to 1, parentheses. Okay, flip over on the back and you try B, same question, and let's see if you get those right. And I have, again, added some arrows there. Okay, so f of x is greater than 0. The y's are greater than 0 when the x's are between -4 and 0. Not that 0. Negative, the x is only -4 to 0. Union when x is 7 to infinity. And f of x is less than 0. This function, these y values are less than 0 here and here. And so the x's that make that happen are from -infinity to -4, union 0 to 7. All right, pause the video again and try this one. Okay, so this is the x-axis here. So this is where y equals 0. So f of x is greater than 0 for the life of the entire function forever and ever. So that's all real numbers, which means that the y's are never less than 0. All right, now let's change the number, but the process is the same. What if it's f of x is greater than -3, greater than or equal to -3, less than -3, less than or equal to -3? Okay, so it's not 0 anymore. We still start the process by graphing, not y equals 0 this time, but y equals -3. And then these are going to be where the graph is above the line y equals 3, and these are going to be where the graph is below the -3. All right, so here is y equals -3. All right, and I'm going to concentrate on the intersection first. So I need to find out where these x's intersect. Okay, so not quite at -5, maybe x is -4.9 right there. They intersect right there. And then right here, that's 1, that's 2, so maybe 1.6. And then here, that's not quite 6. It looks like maybe we'll say 6.1. All right, so now we have the points of intersection. All right, f of x is greater than 3 means where the y is greater than -3. Well, here's where they equal -3, and here's where they're greater than -3. All right, now we're going to write down the x's that make that happen, and since it doesn't say greater than or equal to, it's going to be -4.9, comma 1.6, union 6.1 to infinity. All these x values make those y's greater than -3. The only thing different between 1 and 2 is now it says greater than or equal to -3. So we can add these points because these are where the x values that equal -3. So that's going to be bracket -4.9, comma 1.6, bracket union bracket 6.1 to infinity. All right, I'm going to erase this greater than -3 work here. Don't need to erase the intersection. Same line, y equals -3, and this time, this is where y is less than -3. So now I need to write down the x's that make that happen. So we have to transfer that up to this line here, here, and here. But it just says less than, so we have -infinity to negative 4.9 parentheses, because I can't include that. That's where it equals 3. Union parentheses 1.6 to 6.1. The only difference between 3 and 4 is now I get to add the brackets on those intersections because that's where they equal negative 3. All right, so you try this one and come back. Okay, so the graph, first you graph the line y equals 2, and I extended my parabola up past it so I could think about it better. And the y's are greater than 2 here and here. That's when the x's are from negative infinity to negative 2.5 to 2.5 to infinity. You always have to get right interval notation from left to right. So it has to be in that order. And the only difference between 1 and 2 is now I get to include where x is equal to 2, which is at negative 2.5 and 2.8. So the brackets we use when we want to include those values. Where is y less than 2? What x values are making that happen? That's happening when x is between negative 2.5 and 2.8. Now, if you got something different than negative 2.5 and 2.8, if you decided on negative 2.4, that's fine. If you decided on 2.7, 2.9, that's fine. I'm not going to, as long as it's a good effort to try to see where it lands, it's okay. Okay, the next thing that we can pull off a graph are something called the zeros. Really important in Math 171. So the zeros are just the x-intercepts. Not the y-intercepts, the x-intercepts. The reason they're called the zeros is because, for example, this is an x-intercept. That's at the location negative 4, 0. So the zeros refer to when we let y equal 0. And we're going to do that a lot when we have functions, right? So the zeros of the function are just the x-intercepts of the function. All right, so there are 3 places where this this polynomial crosses the x-axis. So there are 3 x-intercepts. Right? So I just wrote this down just to, if WebAssign says something like this, you have to follow the directions. So it says identify the zeros. We did. Now, the way we're told to write them, we were asked to write them as ordered pairs in order from the smallest x value to largest x value. So sometimes WebAssign will do that so that it could grade you correctly. So we have to follow the directions. All right, so those are what zeros are. All right, the next thing is we're going to talk about increasing and decreasing functions. And the function is increasing whenever the second y, as you go left to right, is greater than the y before it as you move left to right. So it's going to look like this. We first learn about increasing functions when we're talking about lines. That line has a positive slope. It's going up as you go left to right. I always say as you sign your name, if you're going up, that's an increasing line. Well, curves can be increasing too. So like a square root function, that's an increasing function because as you go left to right, each y value is getting higher. So it doesn't have to just be lines. All right, so an increasing function is going up as you go left to right. A function is decreasing if the second y as you go left to right is lower than the y in front of it. So as you go left to right, if you're going down as you go left to right, that's a decreasing function. And again, it can be curves. So that's a decreasing function. All right, and what you'll be asked, it's just like what we were doing. The y values are what increase and decrease. But you're going to write down the x coordinates that make that happen. The inputs make the y's do things. And so you have to write down the x values that are making the y do things. And this can get really tricky when you're graphs are really vertical because it messes with your mind. So we'll do the first one. So this one says, example, estimate the intervals on which this polynomial function is increasing and the intervals on which the function is decreasing. All right, so let's do increasing first. So just like we did with the inequalities, we're going to locate increasing by looking at the y's. So this is where the function is going up as you go left to right. Here. Anywhere else? Yeah, here. All right, now, so to start, you're looking at the function and it's going up. But now we have to change our thinking and we have to think of the x values that are making that happen. So this is a coordinate, negative 2.393, negative 7.674. So when x is negative 2.393, and then this is a point, negative 1.234, 2.512, and when x is negative 1.234, that little area of x is right there. That's where the function is increasing. So you don't write down the y values. I'm going to actually cross through them. For this example, for these increasing and decreasing, it's all about the x's that make the y's increase. So from negative 2.393 all the way, comma, negative 1.234. That's an interval, not an ordered pair. All right, union, there's another area where it increases from when x is negative 0.285 to 0.713. All right, so that's the areas of increase. These are the x values in interval notation that make that function increase. All right, let's erase our increase work and let's do decrease. All right, so we have to locate the y values or the area of the function that's decreasing from left to right. That's right here. And that's very vertical, but it's not exactly vertical. Polynomials won't do that because they're functions. So even though they look pretty vertical, they're not, just because we know about polynomials. So there's 3 areas of decrease right there. What we have to do is we have to write down the x's that are making it happen. Okay, so that's hard because even though that's going to positive infinity, the y's are going to positive infinity. We don't care about the y's. We're changing our thinking to the x's. So this is negative 2.393. And from here on forever and ever, that's where the function is decreasing. And then from here to here, right here, that's where the function's decreasing. And then from here to infinity, that's where the function's decreasing. So that's really tough to make that change. So you're probably going to be like, that's not that tough, Miss Mills. Well, that's because I drew on my picture this. What happens is students don't do that and they're just thinking about that up arrow. But we're writing down the x's that make it happen, and we have to write it down in interval notation from left to right. So we're starting at negative infinity. See, that's what's hard is that's so vertical, but it's not really vertical. Eventually, it'll get to negative infinity. So from negative infinity to negative 2.393, union this x-coordinate negative 1.234 to this x-coordinate negative 0.285, union this x-coordinate 0.713 all the way to infinity. Trickier than it seems. So when you do WebAssign problems, check that out. Just make yourself draw those horizontal lines. We're only writing the x's here. All right, now on the back, the next thing we're going to be asked to pull off a graph are extrema. Okay, so the word extrema means the local maximums, local minimums, absolute maximums, or absolute minimums. And this is where the definitions of these things are pretty important. So believe it or not, I've cleaned this up a lot, but you still have to know what I've got down. This is all important. So the definition of a local maximum of a function occurs when the graph of f changes from increasing to decreasing. So you have to have that change from increasing to decreasing. That gives you a local maximum. All right. A local minimum of f of x occurs when the graph is changing from decreasing to increasing. So you have to have that little mountain or valley. All right. Now, technically speaking, when I ask for the local maximum, it's the y value. The output is a local maximum, just the y value. All right. So when I ask you what the local maximum is for this problem, it would really just be 2.626. And then you could say, well, that happens when the input is negative 1.528. So this technically is the local maximum, just the y coordinate. But we could also, it's often very common just to say, what's the local maximum, and write your answer as an ordered pair. So if that's the case, then we could write the coordinates. So this is an interval notation here. This is the location. It's like latitude, longitude. This is the x coordinate. That's the y coordinate. So a lot of times on the test, we'll say write the local maximum and write it as an ordered pair. But technically speaking, that's the y value. The y value is the maximum, local maximum, and that is where it occurs. Okay, so you see you have that change from increasing to decreasing. That's a local maximum in that area. That's the highest y value. All right. There is a local minimum right here because you have a change from decreasing to increasing. So the local minimum is negative 0.226, and it happens when x is 1.528, but we could ask you to write the ordered pair. All right. This, you might say, is that a local maximum? This is why the definition is important. That's not a local, is that a local minimum, I should have said. It's not a local minimum because it is a low y value, but there's not that change from decreasing to increasing. So endpoints can't be local minimums because you have to follow that definition. All right. But there's another type of maximum and minimum. There's something called an absolute maximum. And that is if this is a y value, f of c, if there's some y value at c that is greater than or equal to all the other y values created by x, all the x's, if there's one y value that's higher than all the others, and that x, for all the x in the domain, then that's an absolute maximum. So that definition is different than the local maximum. There just needs to be a y value that is higher than all the other y values. An absolute minimum. If f of c, if there's a y value at c that's less than or equal to all the other y values at all the x's, then that's an absolute minimum. All right, so look at the graph here, all right? And there is an obvious absolute minimum. And that's this point right here, and that's the ordered pair is -4, -6. So the absolute minimum, the lowest y value of all the other y values is -6 when x is -4. But the question is there an absolute maximum? And there would be, but that's a hole. So technically that's when x is 4, y is undefined. Right? So that means that there is no absolute maximum. All right, so now you try, and I'll label this, it says classify all extrema, so that means state, and just write it as ordered pairs this time. Local min, local max, there can be more than one, absolute min, absolute max. Can't be more than one there. All right. All right, I hope you paused the video and tried these. There is a local min, the ordered pairs, there's one here because see the change from decrease and increase. So that's a local min at -2, -3.2. And then here's another local min, change from decrease to increase, 2, 0. There is a local max right here. We have a change from increasing to decreasing. 0.75 to 0.439, that's the local max. Now, absolute min, is there a lowest y value lower than all the other y's? And that would be here, -2, -3.2. So something can be both a local min and an absolute min. And this one, I added the arrows to make it clear. There is no absolute max because this is going to keep, the y values are going to keep going to positive infinity. All right, pause the video and try this one. Okay, so here there's a local min here, and I think I could read, it's hard to read the numbers, so that's what I got. And there's a local max here. But this is not a local min because it doesn't change from increasing to decreasing. Endpoints can't be local mins, so just have one of each. This time the absolute min is this local min, so that's the lowest y value of all the y values. And there is an absolute max this time right here. Absolute maxes can be at the endpoints because of the definition. That's the highest y value of all the y values on that function. Okay, we have 2 more to try. Before you try, just clear out this. This is a hole here, and there's a hole here, and there's arrows here and arrows here. So determine the intervals when the functions are increasing and decreasing and classify all extremas. So this time you need to do everything we've learned in terms of increasing and decreasing intervals and the extreme. Okay, so this one I just wrote. The numbers are hard to see, so hopefully you could see these. And then I just wrote that's a local max and a local min, that ordered pair. I mean, that's a local max and an absolute max, that ordered pair right there, -1.309, 12.317. And that's a local min right there, and an absolute min, 3.309, -12.317. And it's increasing from, that's -3 to -1.309, that x value. And it's also increasing from 3.309 to 5. It doesn't matter that those are holes because we're not including them anyway. And it's decreasing right here from when x is -1.309 to when x is 3.309. This one, that's -10, 0. This point right here is hard to see. It was 3.333, 23.704. So that's a local max, but it's not an absolute max. And this one is a local min, but it's not an absolute min. So there is no absolute max or min. It's increasing from -10 to 3.333 and decreasing from -infinity to -10 union 3.333 to infinity. Okay, so the next thing we need to talk about is end behavior of exponential functions. At a later time, we're going to talk about end behavior of polynomials, but today we're just going to look at exponential functions. So you have to remember what an exponential function looks like. That's where we have to start. This is not a polynomial. This is a polynomial. It goes on forever and ever. It's nice and smooth and curves. This is a backwards J, and this is looks like a regular shaped J. Those are exponential functions, okay? And the interesting thing about exponential functions is they're in this form, f of x equals a base b to the x power, and the end behavior is determined by b. Okay, so if b is between 0 and 1, like if b is a fraction, b is always going to be positive. So if we have y equals 1/2 to the x power, for example, what's going to happen is it's going to look like this. Now, you don't need to know that right now, but I'm just giving you the example. All right, so given a exponential function like that, you need to understand that what's happening is when it looks like that, that's decaying, it's getting smaller. You can see that as x gets bigger, y is getting really close to this x-axis, which means y is getting really, really close to 0. Okay, so there's something called a horizontal axis, a horizontal asymptote. Horizontal asymptote is, for this problem, y equals 0. There's a horizontal line that this function, this exponential, is trying to touch, but theoretically will never touch it. It'll never get there. It's just going to get infinitesimally close to it. All right. So when you see this graph, what's happening as x, we'll start here since that's what I'm talking about. As x gets bigger and bigger and bigger, y is getting smaller and smaller and smaller. And where's it trying to get to? Is trying to get to 0. So there's a relationship between as x goes to infinity, f of x goes to 0 with this horizontal asymptote y equals 0. Now this doesn't happen with exponential functions as you go in the other direction. As x gets smaller and smaller and smaller, y is going to get bigger and bigger and bigger. Okay, so that's what this says. As x goes to negative infinity, in other words, as x goes to the left, that's what that means. As x goes to negative infinity means as x goes to the left, y is going up and up and up. That means towards infinity. Okay, so let's look at another function. This is exponential as well, but this function, as we go left to right, is getting bigger and bigger and bigger. That happens when b is greater than 1. So that's like y equals 2 to the x. So still has a horizontal asymptote. All exponential functions do, of y equals 0. But this time, as x goes to the left, that's when y is trying to get to 0. So as x goes to negative infinity, f of x or y is trying to get to 0. But as x goes to the right, y is going to get bigger and bigger and bigger. Okay, so that's the end behavior of an exponential function. So let me throw one here at you. I can graph one. I'm going to graph a growth one, and I'm going to give it a translated up, and it's going to look like this. All right, can you see? First of all, you have to say, oh, that looks exponential. And so what I'm trying to get you to see here is that there looks like there's a horizontal asymptote at y equals 3. So you have to kind of locate that. So that means as x goes to infinity, where does y try to go to? And as x goes to negative infinity, where does y try to go to? Do you know? Well, this means as x goes to the right, y is going up, so that one's just going to infinity. But as x goes to the left, where's y trying to get really close to? That's right, 3. All right. The next thing that we're going to talk about, horizontal and vertical asymptotes again. But this time we're going to do it in the context of the rational function. So a horizontal asymptote is a straight horizontal line, always in the form of y equals some number k. So it's always y equals, that's the way horizontal lines are, the equation of a horizontal line are. So don't forget the y equals. It's associated with a curve that indicates that a curve is heading towards the y value represented by a horizontal asymptote as the values of x get really large. That's what I was just doing there, in the positive or negative direction. So example, we just said both functions above have a horizontal asymptote of y equals 0. All right. And because, as in graph 1, as x approaches large numbers, y's value approaches 0. And in graph 2, as x approaches very small numbers, y's value approaches 0. Now, that's one thing. Now, I like to make sure people understand there's a difference conceptually about between horizontal asymptotes and vertical asymptotes. So horizontal asymptotes have to do with very large positive and negative values of x. Okay, so technically a graph can cross through a horizontal asymptote when x is small. It's just where it's going to head as x gets really big. But vertical asymptotes, they're straight vertical lines, always in the form x equals h, associated with a curve that indicates the x values are not in the domain. So the vertical asymptote has to do with restrictions on x. See how different those ideas are? All right, let's look at some examples. All right, so here we have a log function example. So these are both log functions. So what's going on with this is it's kind of tricky because this is going to get pretty horizontal, but what I know about log functions, and now you do too, is that it's never going to level off like an exponential. It's not going to have a horizontal asymptote, but it is going to have a vertical asymptote. Okay, so this has a vertical asymptote. And a lot of people say 0. And if you were in my class, I would say it's not a number. The vertical asymptote is an equation. It's x equals 0. So if you don't put that x equals, you lose a point. All right. Now what that means is, we haven't learned about logs, but I'll go ahead and tell you. This part here is called the argument, that little spot. There's going to be a number in there. Right now it's x. And you're not allowed to put negative numbers or 0 in there. So it's kind of a new domain restriction. X has to be greater than 0. And so that's why that vertical asymptote is there. So that graph will never cross that ever. All right. Same thing for this is a log function that's been flipped upside down. It has a vertical asymptote at x equals 0. All right, so log functions have vertical asymptotes. Exponential functions have horizontal asymptotes. All right, the rational function has both. All right, so interestingly enough, let me give you an example. This is a graph of f of x equals 1 over x. And we have learned that you can't have 0 in the bottom fraction, so we know x cannot equal 0. Okay, so that's going to show up on the graph as a vertical asymptote of x equals 0. Because vertical asymptotes tell you about restrictions. So x equals 0 is the vertical asymptote because x can't be 0. All right, now this horizontal asymptote that you should be able to see here doesn't tell you about restrictions. What it's telling you is that no matter what I put in for x, if I put 100, I get 1 over 100. That's 0.01. That's pretty small. If I put in x as 1,000, that's 1 over 0.001. That's a really small number. And you can see what's going on is as x goes to infinity, y is trying to get to 0. Theoretically, it'll never get there. Same thing as x goes to negative infinity. This time, y also goes to 0. So the horizontal asymptote's talking about in behavior, and the vertical asymptote is talking about restrictions on x. So rational functions have both of those things happening. All right. You pause the video and try to write down the horizontal and vertical asymptotes if they exist. Okay, so I wrote down all my asymptotes, and then I also wrote down, because you're still learning, you gotta recognize these types of functions. This is an exponential function. It has a horizontal asymptote at y equals 5. This is a logarithmic function. It has a vertical asymptote of x equals -5. Now, again, if you didn't hear me the first time, you can't just say -5. I'll count off. It's x equals -5. Same thing here. You can't just say 5. You have to remember horizontal asymptotes go through the y-axis. That's why it's y equals. Vertical asymptotes go through the x-axis. That's why it's x equals. Down here we have a classic rational function. And it has both a vertical asymptote of x equals 5, and it has a horizontal asymptote of y equals 10. Did you catch that? I counted by 5s there. All right, and this one is also a rational function. So these little branches give it away, even though there's 3 little pieces. That can happen with a rational function. There's 2 vertical asymptotes at x equals 10 and x equals -10. And there is a horizontal asymptote at y equals 5. All right, flip over on the back. I got one more thing for you, and that is sometimes we can interpret horizontal asymptotes. They are really good for interpreting in real life. Let me give you an example. So in the following graph, y represents the temperature, internal temperature of a chicken that you put in the oven. After X minutes, when taken, this is a refrigerator. You're taking it from the refrigerator at 38 degrees Fahrenheit. So since the refrigerator is 38 degrees Fahrenheit, so is the chicken. It starts out at 38 degrees Fahrenheit. Okay. And it's put in a 350 degree oven. Okay. So what happens when you put chicken in the oven? As the minutes go by, the input is minutes. All right, input is minutes, X equals minutes, and Y equals temperature of the chicken, okay? And so as you put it in the oven, starts at 38 degrees Fahrenheit, like the refrigerator, and it's going to get warmer and warmer and warmer. Do you see how it's leveling off here? How do I know it's leveling off? Well, because the context clues, I'm putting it in a 350 degree oven. It can't get warmer than the oven, right? So that means there is a horizontal asymptote of Y equals 350 degrees Fahrenheit. All right, so that horizontal asymptote in this context, we like to call it a limiting value. So we might ask you, what is the limiting value for this word problem? What that means is there's something that's limiting the rise in the temperature of the chicken, and that's the oven is only 350 degrees. So to interpret a horizontal asymptote or a limiting value, we're basically going to interpret with English this, right? This is the end behavior notation. As X gets really, really, really big, Y is going to approach 350. So when you interpret, you just turn all of these things into words, and that's where I got I came up with the words Math English Dictionary. So as X, well, what's X stand for? Minutes. As the minutes in the oven increase or get large after many minutes, we might say. After many minutes. Many X's. As X gets really big. But we don't want to say that. We want to use the units. What's happening to the Y? Well, the Y is temperature. The internal temperature of the chicken, and we like to use the word approaches 350 degrees Fahrenheit. So that's how you would interpret. After many minutes, the internal temperature of the chicken approaches 350 degrees. Or as minutes in the oven increases or get large, the internal temperature of the chicken approaches 350 degrees. So we just took that mathy sentence and turned it into an English sentence. All right, so you pause the video, try this one, even though we're given not a graph, but a table. See if you can find the limiting value. All right, so this one, I wrote my Math English Dictionary. That is something that you need to do every time, 100% of the time, even though it's written right here, because it makes your brain slow down and think, okay, my input is hours, my output is amount of yeast. This is the name of the function. So an amount of yeast function in the units or grams. So I put both of those on there. And if you look at the table, you can see that after 5 hours, you've got 119 grams. And as the hours increase, it goes up to 513, but then it starts to increase just a little bit at a time until finally we're talking tenths, 664.3, 664.8, 664.9, 664.98. So you have to infer from that it's trying to level off at 665 grams. So the horizontal asymptote would be Y equals 665. All right, then to interpret it, I said as many hours goes by, that's as X gets to infinity, so many hours. The amount of yeast, because that's what Y is, it's the amount of yeast. And then I just explained what was happening. It's growing at first, but it's leveling off. So that's a word that we can use to describe this horizontal asymptote. It's leveling off at 665 degrees, 665 grams. That's called a limiting value, and that happens in nature. There's only so much space for that yeast to grow, and so eventually it's just going to level off based on the amount that it started off and the space it has. Like if you have fish in a pond, you can only have so many fish in the pond before there's not enough for them all to eat. So limiting values happen a lot in nature. All right, there's lots of homework, so I would do all of these problems and check the key. I've got it posted somewhere, I'm sure.